things to think about here. It says, you want to do a kinetic versus thermodynamic enolate here, right? We want to make sure that if we want to get the kinetic enolate, and it's going to be, I think, on back over here in our notes here. Let's see if I can find it here. What? Let's see what I did with it. Mouse. Let's go ahead and talk about this a little bit. Kinetic versus thermodynamic enolate. So like I said, if we want to form the kinetic enolate, we're going to use excess LDA. And remember what we said, that with LDA, if we draw, let's use the right color here. Let's draw our compound out. It'll be easier to see this way. Okay, so here's our starting material. We have a CH3 over here. In the future, I'm just going to represent that by a line. And then we have H's over here and also over here. And we said if we want to form the kinetic enolate, which looks like this, then we use excess LDA. Now remember, LDA is lithium diisopropylamide. So we're going to have two isopropyl groups, negative charge on the nitrogen, and what this thing is going to do, it's going to come up and deprotonate the compound and form our enolate. And this happens in excess LDA. Why? Because this is the less hindered side, and this enolate will form faster, which we'll term kinetic control. But how do we get to, let's say, thermodynamic control? So what I'm going to do is we're going to kind of like, I'm going to grab this. I'm going to see if this will, let's even put in a duplicate page. That should do it. So let's say there's a duplicate. This would still form really fast, but what happens under the, let's say, thermodynamic control, because you have excess ketone, this is going to bump into more of your ketone. And here's our CH3, and I'm going to put the H here. So what happens is the enolate can now deprotonate the excess ketone to give us our thermodynamic enolate. Now realizing that we also get what? Reformation of our starting material. Okay? So again, thermodynamic control, and we'll label this slide as such. So thermodynamic control. We use what? Excess ketone. We still form the kinetic enolate, but then that bumps into more ketone to form our thermodynamic enolate instead. As opposed to over here where we're under kinetic control, where because there's excess LDA, you come in from the less hindered side and you form the kinetic enolate. Okay, we only have one last thing to look at, actually two things. Problems with aldol condensations. The only problem I want you to remember for aldol condensations is that one of the compounds cannot have protons available for enolate formation. If they do, you're going to have a big mix of products. So you pick one compound, like acetone, that has acidic protons, it can be removed to form enolate, and the other compound, like benzaldehyde, that does not have any. Now, here's a mechanism of acid chloride formation with the thionyl chloride. We have a pair of electrons on the O attack the sulfur because it's partial positive, kick out chloride. Second step, chloride deprotonates and eliminates the positive charge in the oxygen. Then we have assistance by this oxygen to form more chloride. And then the last step, chloride comes back and releases our final product plus SO2 gas, which bubbles out, and our other byproduct is HCl. Now, I'm pretty sure that covers everything on our review. I guess the only other thing we could do is says, you have an aldol condensation here, and this is the one we kind of did in class, so please go back and review this one again, and that problem will be up on the notes.